right, welcome to section 3.8. This will be our last differentiation technique section of chapter 3. We will then evolve into some related rate problems in section 9, and then we move on to chapter 4. So for our last technique, all functions we have seen to this point have been functions where y is defined explicitly as a function of x. So y equals 3x squared minus 2x plus 10 or something like that. It is y is equal to everything in terms of x. However, relations between variables are often expressed implicitly, which means they could have things that are mixed together with x's and y's. For example, the equation of the unit circle, which is x squared plus y squared equals 1, is an implicit relation there. It's not a function because it is a circle. Now, if I were to solve for y, then to get rid of that square, I'd have to square root both sides. That would result in two explicit functions for that. Now, once you have two of those, one would be a plus, one would be a minus. You have a square root. It is kind of tedious in order to differentiate. So, also, some other implicit functions may not be easily solved for y. So we have to have some way to be able to take a derivative of all those other functions as well. Now, the goal of this section is to find a single expression for the derivative directly from an equation without having to solve for y to begin with. This is what we call implicit differentiation. Now, this is also kind of a precursor also to when we start going backwards, when we do some integration problems. So being used to implicit notation is really, really good. Now, we will do this by example. So the first ones I'm just going to do are just these two very simple monomials. The derivative with respect to x of x cubed and the derivative with respect to x of y cubed. Now, what you want to be conscious of here whenever you're doing implicit differentiation is to see if our variables match. These are the same variables, and everything that we've done up to this point has been basically with respect to x. And so when we take the power rule of this, when we have what is the derivative of x cubed? Well, we bring the power out front, decrease it by 1, and get 3x squared. So when the variables agree, when they are the same, we're going to straight use a power rule for this example. Okay, now not for all examples. If it's a product, we'd have to do a product rule or a quotient rule. But in this example, the variables don't agree. So therefore, we have to use a notation to be able to kind of chain rule that in an implicit way. So here's where we are going to use implicit differentiation when we do something like this. Now, what we do is we still use the power rule, but we're doing it in terms of y. Then we have to then take the action to take the derivative with respect of the derivative of y with respect to x. So I'm going to take this just as is with the power rule. That would give me 3y squared. But then I have to chain rule the inside because if this is a function of x, I'm going to have to take the derivative of that function with respect to x. So that's the implicit part that comes into. And that should be a times there because you are timesing that. Obviously, you don't have to write the times, but reiterating the fact that you are multiplying those together. Now, there are some instances in which that notation sometimes gets a little bit tedious. So I will tell you that most often than not, I will use the y prime notation for the derivative of y with respect to x. Okay? So that's just a small version. Anytime you have different variables, you must use implicit. Okay? If they are the same variables, you do it as is what we've done before. Okay? So let's look at this first example. We want to calculate dy over dx. The derivative of y with respect to x is the way we could also state that. Directly from the equation of the unit circle. Now, we wrote in the equation of the unit circle above. It is x squared plus y squared equals 1. And we want to find the slope of the unit circle at this point. So that, maybe you recognize that as the point on the unit circle at a 30-degree angle. And also at a, I don't know. Let's see, where would that be? Oh, it would also, no, that would be the 30. I'm thinking of, never mind. All right, so here we are going to take the derivative of this equation. This is one that you could solve for y equals, but you're going to get two different explicit equations that you have to differentiate. So we're going to use implicit to do this. So I'm going to find the derivative with respect to x. That x is very important because if you agree with that variable, there's no other thing to do besides do the derivative. If you disagree with that variable in the bottom, that's where we have to add the dy over dx or the y prime. So this one we're going to do with the dy over dx. All right, so here they agree. So we're going to then do 2x as my derivative of x squared. Then they disagree, and so I must then take that extra piece. I'm going to take the derivative of y squared to give me a 2y, but then I have to multiply that with respect to x of that function or of that letter. So we would then have the dy over dx. Now, what is the derivative of 1? Well, it's a constant, therefore that derivative is 0. So at this point, if I'm saying to calculate what dy over dx is, now I have an equation with dy over dx in it. I can solve for dy over dx, and that would be what it's equal to. So in order to get this by itself, with it being two terms that are added, I'm first going to subtract over this term. And I get 2y times dy over dx is equal to a negative 2x. And then I'm going to divide, because if these are all multiplied together, if I want to get this by itself, I'm going to divide by everything but that. So I'm going to divide by 2y. These go away. Therefore, dy over dx is equal to, simplifying this expression on the right-hand side, I can cancel my 2's out, and I have a negative x over y. And that right there is the derivative of our relation for that unit circle. So that means that now if I ask you for the slope of the tangent line, which is what we're getting ready to do, then you can find it given an x and a y. But you have to have all the values of the point. Now, if they're only given x, you can plug it into the original function to find the y. So there's ways to get the y if they don't give it to you directly out front. But then, once we know that, we could also then write the equation of the tangent line as well. Okay, so lots of things we can do that are similar to what we've done before. So now let's go ahead and find the slope of the unit circle. So m, which is equal to our dy over dx, is equal to the opposite of x over y. So the opposite of x is negative 1/2 over the y value, which is root 3 over 2. And at this point, you can rewrite the first one and multiply by the reciprocal of the second because you're dividing two fractions. Or if you are one that likes to do the extremes over means, then you can do that as well. So a negative 1 times 2 is a negative 2 over 2 times root 3. I'm just going to rewrite it like that. And notice we can simplify one more time by canceling out our 2's, be left with a negative 1 over root 3, which, if you rationalize, or if it's requested of you to rationalize, would be negative root 3 over 3. So either one of these answers would be fine with me. In my lab math sense, whenever you are doing a multiple choice problem, you would definitely want to make sure that you chose the correct one. All right, very good. So let's try a couple more of these. And this, again, can include all different types of techniques that we've done so far. It could include the chain rule, could include the product rule, could include a quotient rule in some cases. So you want to make sure that you're mastering those techniques first before we get into this as well. All right, so here we go. We have a relation equation here as x squared plus xy minus a y cubed equals 7, and we're out to find dy over dx. I'm going to replace that from here on out with y prime just because I don't like to write those fractions. I think it gets kind of confusing. But this could also get confusing as well because if you aren't neat with your writing and you drop that prime on that y, then things could get a little crazy, okay? So, all right, so here we go, dy over dx. We're looking for all the matching terms of x. And we're going to take that derivative as is. Anything that's different than x, we have to do the y prime with. All right, so we're going to take the derivative of x squared, which is 2x. Now, I encounter x times y, so I have to take the derivative of that. Now, that is a product rule, letting x be my first function, y be my second function. Now, it is also important to note here that if this is a minus and you're getting ready to kick out two terms from this derivative, you want to make sure that you distribute that minus. Maybe I should change it into a minus on this one, but I'm not. So be cautious if that's a minus in front of a product rule. So we're going to keep it as a plus. So we're going to take the first times the derivative of the second. Now the derivative of just y is 1, but it is a variable that doesn't agree with our x. So I would then, you can multiply times 1, but y prime. Also, I probably wouldn't necessarily write the 1 all the time, but for this first time, maybe I do for you. Then we're going to add to that the second times the derivative of the first. So the second is y. The derivative of the first, now that's a variable that matches our x, so we're just going to make that a 1 for its derivative. Minus the derivative of y cubed, doesn't match my x, so I have to include the y prime. Derivative of y cubed is 3y squared, but then I have to include that y prime for my implicit differentiation, equals to the derivative of 7, which is 0. Okay, so I'm going to kind of rewrite this without kind of getting rid of some of those 1's. I get 2x plus xy prime plus y minus 3y squared y prime equals 0. Now, our task is to get y prime by itself. Notice I do have two y primes that are added or subtracted together. In this case, we're subtracting by that 3y squared y prime. So we're going to have to do some factoring stuff in order to factor out that y prime. But in order to be able to do that, I got to get rid of this term to the other side. So I'm going to subtract y, and I'm going to subtract over that 2x. So the right side becomes a minus y minus 2x, or a minus 2x minus y, however you want to do that. And then I'm going to factor, go ahead in this same step, factor the y prime out of those two terms. So when I do that, take a y prime away from here, I'm left with an x. Take a y prime away from here, I'm left with a minus 3y squared. And now we're ready to go to be able to get y prime by itself. So since this is a product of two things, then I can divide by that term. So I'm going to divide by x minus 3y squared. Divide by x minus 3y squared. And this right here is my y prime, because these cancel out. So y prime is equal to minus y minus 2x, which you could actually take out a negative if you want. That is an answer that you have to choose from. They may take a negative out, so making sure that you know that those are equal. So that's our y prime. That was the slope of our tangent line. That's our rates of change of our function in terms of x. Okay, all those things mean the same thing. All right, let's do a couple trig functions here, and then we'll write an equation of a tangent line. So I have sine of xy is equal to x squared plus y. Obviously, the right side is going to be much easier than the left side. The left side is actually having two different functions. I have this function and that function. So that incorporates a chain rule that we learned in last section. The outermost function is sine. The innermost function is this x times y. So I have to take the derivative of sine in terms of this function. So the derivative of sine is cosine of xy. But then I have to take the derivative of the inside piece, which actually we just did over here. Okay, so I'm going to probably eliminate the 1's this time. So I'm going to take the first times the derivative of the second. So the first, the derivative of y, remember we're looking for dy over dx. When we get to a y, it doesn't agree with what variable we're taking the derivative with respect to. So I have to take the derivative of y, which is 1, but then I have a y prime that I have to incorporate with that implicit piece with respect to x. Then I'm going to add to that the second times the derivative of the first. So the y times the derivative of x, which is 1. We don't need anything because those variables match. Equals derivative of x squared. No implicit needed here because that matches with our variable in the bottom. And the derivative of y is a 1, but I have a variable that doesn't agree, so I need a y prime. All right, very good. Now that's the calculus part. From here, it's algebra. We got to get y prime by itself. Y prime exists right here, and it exists right here. But on this left-hand side, I have this trig function that I'd have to distribute through both of these. So I'm going to go ahead and do that. I'm going to get, go x cosine of xy times the y prime. I'm just going to put the y prime at the end. Then I'm going to multiply this times this. Gives me plus y cosine of xy is equal to our 2x plus y prime. So we're going to have to do a little bit of factoring just like last time. So that means that this term I'm going to subtract over here, and this term that doesn't have a y prime to subtract over here. So you kind of move things around where you can get all the y primes on one side, everything else on the other. So that becomes x cosine of xy times y prime. And what did I subtract over? I'm subtracting over this y prime. So I'm going to get minus y prime is equal to this 2x that I'm subtracting over this second term. So I would then get a minus y cosine of xy. So again, be very meticulous here when we are bringing things down with our algebra. So at this point, now that the y primes are on one side, I'm going to factor out a y prime and be left with x cosine of xy. When I take that y prime away, then I'm just left with these two terms, minus, if I take all of that out, I'm minusing a 1, is equal to nothing changes on the right side. And we are almost finished because in order to get y prime by itself, I have to do a little division by this expression. So I'm going to divide this both sides. So I'm going to say that y prime is equal to all of this divide by everything in the expression. So 2x minus y cosine of xy all over x cosine of xy minus 1. And that right there would be our final answer. Now, obviously, if I were to ask for the exact slope at a certain value or a certain point, then I would have to give you an x value at least. And then you could, from the original function, find out what the y value is. Again, sometimes those are a little bit more tedious than others, especially when you have some of these trig functions. So that would be our slope of our tangent line or our first derivative for that given function. All right, that one was pretty involved. Let's try this next one. We have 2 sine of x times cosine of y. 2 sine of x times cosine of y. Again, we're looking for dy over dx. So anytime we take a derivative of an x, we don't need anything extra. But when we take a derivative of a y, we do need something extra, which is that y prime. So I'm going to treat this as 2 functions that are multiplied together and use the product rule. So I'm going to treat 2 sine of x as my f function and cosine y as my g function. So for the product rule, we're going to take the first times the derivative of the second. So the derivative of cosine is actually negative sine of y. But since that is the letter that doesn't match the x, then I have to include a y prime. Plus the second, which is cosine of y, times the derivative of the first. So the derivative of the first, I'm going to keep the constant out front, but then just take the derivative of sine, which is cosine. So that's going to be 2 cosine of x. Now, that is equal to, derivative of 1 is 0. So this one's actually pretty nice for us to kind of put things together. But first, I kind of like to clean things up a little bit. So again, here's my first times the derivative of the second, plus the second times the derivative of the first. And the only time I took the derivative of this to engage a y prime is right here. So I'm going to clean this up and let's go minus 2 sine of x sine of y times y prime. You can't put those together because they have different angles, so it's not like a squared or anything. Plus 2, I'm just going to do cosine of x cosine of y, keeping alphabetical. And that's equal to 0. Okay, so we got to get y prime by itself, which is in this term. I'm going to think about adding that term over. Since it's negative, I'm going to add that 2 sine x sine y, y prime over. So what I get is 2 cosine of x cosine of y equals 2 sine of x sine of y times y prime. And these are nice because they're all multiplied together. So when I need to get y prime by itself, which is right here, I'm going to divide by 2 sine of x, sine of y. And I'm going to divide on the left side by 2 sine of x, sine of y as well. And so on the right side, everything cancels except for the y prime, which is good. Sorry for the delay. So here, this goes away, that goes away, and this goes away, leaving me with a y prime on here is equal to, which is the same as dy over dx. Now my 2's are going to go away, and I'm left with cosine x cosine y over sine x sine y. Now, if I were to box out a couple of these and bring to your attention that I have the cosine of an angle over the sine of an angle, can we replace that by something that we know in our identities for our trigs? Well, the answer is yes. Cosine over sine is defined to be cotangent. So I'm going to write this as the cotangent of x times the cotangent of y, and that will be my final answer. So, again, depending on a test for me or in my lab math, depending on what they actually give as answers, it was to kind of figure out how far that you need to go. On a test situation, if I wanted to get you down to here, I would say prove that this is equal to that for its derivative. And so you would have to show me step by step for that to occur. Okay? All right, so let's do this last one before we get into doing a second derivative using implicit differentiation. Here we want to find the equation of the tangent line at 1, 1. So here I'm giving you an x and I'm giving you a y. So we want to first, we have to find the equation of the tangent line. We have the point, but we don't have the slope of the tangent line, which is the derivative. So we have to find y prime or dy over dx for this function. As it is implicit. So here we go. We're going to take the derivative of x squared, which is 2x. And again, we're doing dy over dx. That's what we're finding first. So if I take a derivative of an x, I don't need anything extra. If I take a derivative of a y that doesn't match with this x, I do need the extra. So that's what we're going to do in this next derivative. So I get 3y squared times y prime for that one. And that's derivative of 0 is still 0. So what I need to do is get y prime by itself. So I'm going to think about adding this term over. So I get 2x equals 3y squared y prime. You can subtract the 2x. That'll get you the exact same answer. And then I'm going to divide by 3y squared and divide by 3y squared to get y prime by itself. So the 3's on the right-hand side go away, and the y squareds go away, and I'm just going to kind of reverse it back. Whoops, y prime, get rid of that. So y prime is equal to 2x over 3y squared. So that's the slope of the tangent line at any point on that graph or on that relation, and we are given for the point 1, 1. So at 1, 1, then y prime is equal to 2 times 1 over 3 times 1 squared. And when I do the math there, that gives me a 2 on top and a 3 on bottom. Therefore, my slope of my tangent line is 2/3. And just like what we've done before, I now take that slope, I now take that point, and I write the equation of the tangent line. So y minus 1 is equal to m times, whoops, I can replace that m, I'm so used to saying it. I can replace that m because I know what it's equal to. It's equal to 2/3. So I'm going to put 2/3 in there, times x minus the x value, which is 1. And I can now distribute that 2/3. Y minus 1 equals 2/3 x minus 2/3. And then the final step to get y by itself would be to add over 1, which is the same as adding 3/3. So if I have negative 2/3 plus 3/3, then I end up with a positive 2/3 x plus a 1/3 whenever I finish at the very end. So that would be the equation of the tangent line to that relation, or to that function. It would be a function, actually. I could look at it real quick and say it's a function. That would be the equation of the tangent line at the point 1, 1. Okay? All right, very good. And our last problem for our implicit differentiation is to be able to take a second derivative of y with respect to x. And so it is getting to be a little bit more involved when we do this. So there are kind of some couple steps that I've kind of just outlined for you. First, you want to find y prime. Then from that, simplify it down as far as you can. From that, find y double prime. And then, once you start simplifying with some algebra, you're going to have a y prime that you are going to sub in the y prime that you got in step 1 into the y double prime that you get in step 2. And then we are going to sub in the original, what the original is equal to, into the y prime. So we'll do that by example here for you with that. All right, so here's our relation. X cubed plus y cubed equals 28. So we want to find the second derivative of y with respect to x. So anytime I have an x, I don't need anything extra, but I do need something extra when I do this derivative in terms of y. So let's take the derivative of x cubed, which is 3x squared, plus, here comes our extra, we get 3y squared times y prime, and the derivative of a constant is 0. Don't forget to make that 0. That's what I see a lot of times as students keep that as 28 instead of changing it to 0. All right, so let's subtract over the 3x. So I get 3y squared y prime is equal to minus 3x squared. Then I'm going to divide by 3y squared, divide by 3y squared. These go away, and we're left with y prime is equal to, these 3's also go away, so I'm left with minus x squared over y squared. Okay, so that is our first derivative. But in anything, here we have to find the second derivative. So our second derivative, and we're going to symbolize that by y double prime, has to come from a quotient. That is a fraction there, so it is going to be using the quotient rule to find the second derivative. So that's a little bit of our ho-de-hi stuff. So we're going to take ho, which is the denominator, times the derivative of the top. Now remember, anytime we take a derivative in terms of y, we have to add in that y prime. Well, we haven't taken a derivative of y yet. So ho d-hi, so this is in terms of x, so I'm just going to keep a negative 2x, minus hi, which is a negative x squared, d-ho. So here's where I got to take the derivative of y. So I'm going to do a 2y, but my implicit part has to be engaged here as my y prime, all over ho-ho, which is the denominator squared. So if I do y squared times y squared, I get y to the 4th. Now, at this point, I'm going to go ahead and clean up a little bit before I do step 3, okay? So here, finding y prime, there's number 1. Let's clean up, and then we'll mark number 2. So second derivative, when I clean up this top piece, is minus 2x y squared. Then a negative times a negative is a positive. And then I get 2x squared y prime, all over y to the 4th. Now, if you look on the top, I do have a y prime. So this is actually step 2 here is where I'm finding y prime. But in step 3 it says we need to sub y prime in to the y double prime. So that means right here I got to take that out and put this in, because that's what y prime is equal to. So I need to put a negative x squared over y squared in for that. So we're going to do y double prime equals negative 2xy squared plus 2x squared y, open a parenthesis, and let's go negative x squared over y squared, all over, don't forget, our y to the 4th. Now, here's where we, again, have to do a little bit of our algebra. Notice here, this is technically on top. I could put that over 1. I have a y here and a y squared, so I could cancel out one of those within there, so I could cancel that y with 1 here and leave me with a y in the bottom. And so if I do that, I'm going to go ahead and kind of get a common denominator. Put that over 1. I can combine this with this all over the y times a 1. So y double prime now is equal to, I'm going to keep minus 2xy squared. But this next term, notice I have a negative here and a positive. Everything else is multiplied, so I'm going to change that back to a minus. I get 2x squared times x squared, so I get a 2x to the 4th all over just that y that I have left over in the bottom. Now, again, it's all over y to the 4th. All right, now, again, this is some complex fraction work that we have. So I'm going to bring this up here a little bit so we can simplify. So notice here, I need a common denominator. To be able to put these two things together, I need a common denominator, which is a y. So that means that I need to multiply this by a y, which means I multiply the top by a y. And when I do that, y double prime is equal to, looks like a minus 2xy cubed minus the 2x to the 4th all over the common denominator, which is a y. But remember, I still have that y to the 4th, so I'm going to put that all over y to the 4th, and I'm going to go ahead right now and put that over 1. So what I have is a complex fraction that I can now simplify a little bit more, okay? Doing the extremes over means, or you can multiply by the reciprocal. So when I do the extremes over means, notice that I do have some common terms up here. When I multiply by 1, I still get back the same thing. Now notice there's a negative in common, there's a 2 in common, and there's an x in common. So I'm going to go ahead and choose to take out a negative 2x, not a negative 2xy, a negative 2x. And when I do that, what am I left over with? Well, negative 2x, I'm left with a y cubed. If I take a negative 2 and one of these x's, I'm left with a positive x cubed all over the means this time, which would give me this y times a y to the 4th, which is y to the 5th. All right, very good. Whew, that was a lot. All right, where did we sub in y prime into y double prime? I believe it was back here. So here's step 3. But step 4 says that when you keep simplifying, that you will get your original equation in this y double prime. And so that's where our last step is I need to sub in what x cubed plus y cubed is equal to right into that double primed y. Right here is that x cubed plus y cubed. So I'm going to extract that out and make that a 28. So I get y double prime is minus 2x times a 28 all over a y to the 5th. And we are one step away from simplifying what our double derivative or our second derivative is with respect to x. So I'm going to multiply 28 times negative 2 and get y double prime is equal to negative 56x over y to the 5th. And that would be our final answer. I know that's a lot, okay? But it's really good algebra exercises to be able to figure those out and to be able to break them down to what is needed, okay? So that would be our y double prime for that problem. All right? So that's all that I have for you for section 3.8 on implicit differentiation. Like I said at the precursor part, section 3.9, the next one we get into is kind of doing some more applications and being able to use some of this implicit differentiation when we are working with relations that not necessarily are written explicitly in terms of x. So until next time.